Let's do a quick problem to put into practice the equations for solving problems in angular kinematics. Here's an example problem involving a potter's wheel. So you can see in the picture it shows that the potter's wheel is rotating in a counterclockwise direction. And let's just make up a value and say that initially the wheel is spinning at a rate of 200 RPM. And somewhere at the base of the potter's wheel is a motor that we'll say controlled by a switch and then is plugged into the wall, and the switch is moved to the off position, and that produces a little bit of a deceleration because of the internal friction in the bearings. So we'll just make up another value and say that the angular acceleration is equal to negative 1.9 radians per second squared. So we'll ask two questions. One, what's the angular displacement expressed in rotations as it comes to rest? And two, how much time does this process take? So to get more familiar with the study of angular kinematics and to help us work our way through the problem, let's just list all of the equations that we know for angular kinematics. So we have one equation that says final angular speed equals initial angular speed plus angular acceleration times time. How about displacement is equal to average angular speed multiplied by time? Or the other way to find displacement, initial speed times time plus 1/2 acceleration times time squared. Final angular speed squared equals initial angular speed squared plus 2 times angular acceleration times displacement. It would also be helpful to make a list of everything that we know and the one thing we're trying to solve for. So we're given an initial angular speed. We're assuming a final angular speed of 0 because it's referencing coming to rest. We're given the angular acceleration, and we're asked for the displacement. So first things first, let's get the units to agree. We're given acceleration in radians per second squared, but we're given speed in revolutions per minute. So let's convert and get the initial angular speed in the proper units. So 200 revolutions in 1 minute. If we want to get rid of revolutions and change to radians, then we need to make sure that this whole conversion factor is simply equal to 1. And that'd be true if we said there's 2 pi radians in every 1 revolution. And we can round off and call 2 pi 6.28. Now we also need to get rid of minutes. We can do that by putting minutes in the numerator in our next conversion factor and change from minutes to seconds. There are 60 seconds in 1 minute, so this conversion factor is really just, again, multiplying by 1. So in the end, we have to take the number 200, multiply by 6.28, and divide by 60. And when you do that, you find an initial angular speed of 20.94 radians per second. Okay, so let's fill that into the list of known quantities. 20.94 radian per second, and the acceleration is negative 1.9 radians per second squared. Okay, so notice in our list of givens we don't have time. It's not asked for yet. We'll have to figure that out in part 2, but for now it's not asked for and we don't know it. So we want to pick the equation that doesn't incorporate time, which is the last equation in our list, because we're asked to solve for the angular displacement. Then we need to do the algebra to isolate, and when we do, we find that the angular displacement is the final angular speed squared minus the initial angular speed squared divided by 2 times the angular acceleration. If we plug in the given values, this becomes 0 minus 20.94 radians per second quantity squared divided by 2 times negative 1.9 radian per second squared. The negatives cancel out. Let's check the units. We're going to have radian squared over second squared divided by radian per second squared. Hey, this looks right. It leaves us with radians as the answer. And if you grab your calculators and try to find out the numerical portion of the solution, I think you'll get 150 115 radians. Although I'm not sure I should circle that as the final answer. The question's asking for the angular displacement in rotations. So 115 radians over 1. Now I need to change from radians into rotations. So there are 6.28 radians in every one rotation. So our final answer should be written as 18.3 rotations. Now, part 2 asks us to solve for the time, and we can now pick any one of these equations. They all have time involved, and we know all of the other kinematics quantities. This is probably the simplest of the equations to work with, so let's use that to finish the problem. If the final angular speed equals the initial angular speed plus acceleration times time, then time is just the change in the angular speed divided by the angular acceleration. This is 0 minus 20.94 radian per second divided by negative 1.9 radian per second squared. Radians cancel. The units look like they're going to come out to give us just what we want, some number of seconds, and your calculator should yield an answer of 11 seconds. So there you have it, just a quick example problem on how we apply the equations for angular kinematics.